All right, so now let's just prove a theorem that sort of collects together all of the kind of familiar rules of differentiation that you remember from calculus, although not the chain rule. So we'll do the chain rule separately, but this will be rules for things like if you multiply two functions, or if you add two functions, or if you divide two functions. So any kind of like arithmetic operations will pretty much be covered with this. And then, and then once we have the chain rule, of course, that will allow us to kind of build up, complicated functions and know that they have derivatives just because they are built up from simple functions that have derivatives using these operations. So here's the theorem. So this is 28.3. So it's four things. So, well, let me write the hypotheses first. So let f and g be differentiable at a. Then each of CF f plus g, where c is a constant, f over g, or sorry, fg and f over g is also differentiable at a, except f over g if g of a, or g prime, or sorry, if g of a, what am I talking about? If g of a equals 0, since f over g is not defined at a in this case. So note that like differentiability, because in the difference quotient, sorry, this is like a sort of a side note, but in the difference quotient, we're looking at the limit as x approaches a of f of x minus f of a over x minus a. So notice that like this requires f to be defined at a, right? Like just inherently from the way it's written, the fact that f of a is included here, f must be defined at a, right? So yeah, in this case, this is not a case where the limit only depends on the behavior of f at points where x is not equal to a, because that's just not true. So yeah, f has to be defined at a. I mean, it has to be continuous at a actually, but it at least has to be defined there. So so yeah, that's why if g of a is 0, even if f over g actually has like a removable discontinuity at a and would become like a differentiable function, right? It's like something like if f was like x, like x over x, for example, right? That's 1. If you think of the constant function 1, like that's a differentiable function, but this is technically not differentiable at x equals 0. Okay, so not differentiable at x equals 0. Okay, even though like everywhere else it's defined and it has like slope 1, it's just not differentiable at x equals 0. Okay, anyway, so yeah, that's the condition for the quotient. So then we have these formulas. So CF prime, oops, the prime should be outside, is C is F prime. CF prime of A, and yeah, CF prime of A, and then this is CF prime of A. Then the sum, of course, So the first two here express the linearity of the derivative. So this is f prime of a plus g prime of a. Then we have the famous Leibniz rule for the product. So fg prime of a is, let's see, f of a, g prime of a. I just want to make sure I get the terms in the same order that they do. Plus f prime of a, g of a. And then lastly, the quotient rule, f over g prime of a equals g of a f prime of a minus f of a g prime of a over g squared a if g of a not equal to 0. Okay, so let's prove this. The first two are basically trivial, so proof. So for x not equal to a, we have CF x minus CF a over x minus a equals c times f of x minus f of a over x minus a. Since the limit of the difference quotient f of x minus f of a over x minus a exists, then the limit as x approaches a of CF of x minus CF of a over x minus a equals c times the limit as x approaches a of f of x minus f of a over x minus a, which is CF prime of a. Okay, very, very easy. Yeah. So, I mean, this is just like trivially from, you know, a limit theorem from, you know, section, I think 20, where we introduced limits. Yeah. So the limit theorems from section 20, you know, give us things like this. So similarly for 2, you know, f plus g of x minus f plus g of a over x minus a, that equals f of x minus f of a plus g of x minus g of a over x minus a, which equals, you know, f of x minus f of a over x minus a plus g of x minus g of a over x minus a, right? So since these two individually have a limit as x approaches a, that means that the sum has a limit, and the limit is the sum of the two individual limits, right? So f plus g of x minus f plus g of a over x minus a equals the limit of f of x minus f of a over x minus a plus the limit of g of x minus g of a over x minus a, right? This is as x approaches a, x approaches a. So this is f prime of a plus g prime of a. This is, again, you know, section 20 limit theorems. I think they might cite it specifically, right? 20.4 specifically gives us this, right? So since these two individually exist, the sum also exists. Okay, great. So those are pretty easy. This one is only slightly harder, and it uses a trick that's probably kind of familiar by now. So in this one, so for the product rule, we can write fg of x minus fg of a over x minus a. You can introduce two terms that cancel out. So you can get like, so we have f of x, g of x is the first term, right? F of x, g of x, right? And then you can introduce minus f of x, g of a, plus f of x, g of a, minus f of a, g of a, okay? This is all over x minus a. And then if you separate these two, separate these two terms from these two terms, then you can factor f of x out of the first two. So you get f of x, and then you have a g of x minus g of a over x minus a, plus, and then this one you can factor out g of a. So we have g of a, f of x minus, f of x minus f of a over x minus a. So this approaches a, this approaches g prime of a, this obviously approaches g of a trivially, and this approaches f prime of a, right? And this here, this is actually by the theorem we just proved, right? So by 28.2. So that's not like trivial. I mean, that's not actually included in the assumptions, right? We only assumed that f and g were differentiable at a, but that means that they're continuous there. So the fact that f of x approaches f of a comes from theorem 28.2. And then, of course, we can use, so by more, section 20 limit theorems, we have that the limit of this difference quotient of the product, fg of a for x minus a equals, you can just move the limit into like each of these things individually. So you have a limit times a limit plus a limit times a limit. And you just get f of a, g prime of a, plus g of a, f prime of a. Okay, great. All right, last one. So the way they do the quotient rule, I'm just going to do it a little bit. So let's show that 1 over g prime of a equals -1 over g prime of a squared. So, or sorry, that's not what I mean. What am I talking about? It should be negative g prime of a over g of a squared. So negative g prime of a over g of a squared. Sorry, running a little bit low on sleep, let's say. Okay, so yeah. So that way, so then like the case for a general like f over g would follow from this using the product rule. So then the formula for f over g prime of a follows from this and the Leibniz rule. Okay. So for this one, it just cleans up the algebra basically. So here it's like, okay, let's take 1 over g of x minus 1 over g of a over x minus a. That equals, so we'll have, sorry, so let's multiply by g of x, g of a on the top and the bottom. So this is g of a minus g of x over g of x, g of a, x minus a. So this is 1 over g of x, g of a, times negative, times the negative of g of x minus g of a over x minus a. Okay, then this approaches 1 over g squared a, right? And this approaches negative g prime of a. And again, this is, you know, by 28.2, I guess. And then, of course, and, you know, section 20 limit theorems. So yeah, anyway, so I guess, yeah. So this is how you get the, right? I mean, so again, like you can just combine these section 20 limit theorems to, and the fact that G has to be continuous and the fact that this limit exists, right? They all combine to tell us that this formula is true. So yeah, there you go. That's those are the familiar rules for sums, products, quotients, you know, constant multiples of differentiable functions, and how those operations affect the values of the derivative. So just as some examples, or just let's look at this one example that they have. So say h of x is x to the minus m, where m is a positive integer, and you know the domain of h is everything except x equals 0, which is of course the default domain of h, because that's the biggest domain possible. Then h of x equals f of x over g of x, where f of x is 1, g of x is x to the m. We know f prime of x equals 0 for all, I mean, that's just trivial pretty much, for all x and r. G prime of x is mx to the m minus 1, as we showed earlier in this lecture, right? So for x not equal to 0, and this is also like not equal to 0 for, or sorry, I should say g of x itself is not equal to 0. So by 28.3 part 4, which was the quotient rule, we have h prime of x. Well, yeah, let's keep the x's and a's straight. Sorry. So let's make these all be a. I guess this can also be a, whatever. So a. So h prime of a would be g of a, f prime of a, minus f of a, g prime of a, over g of a squared. And that is a to the m times 0 minus 1 times m a to the m minus 1 over a to the 2m, which is equal to negative m over a to the m plus 1, or negative m a to the negative m minus 1, if you prefer. So this is the power rule, what you might call the power rule for, there's an A here. What you might call the power rule for, function, negative powers of x, basically. Yeah. So that is all for this video. And in the next one, we'll start to look at the chain rule, which is rather more subtle and complicated than you might expect or hope for.